Hello students, welcome back. Let us resume our discussion in section 2. Previously we completed up to 2.4, so let's resume from 2.5. Perfect numbers. A positive integer n is called perfect if sigma n is 2n. In other words, what's the definition of sigma n? The sum of all positive divisors of n add up to 2n. Equivalently speaking, the sum of all positive divisors of n other than n itself will add up to n itself. Here are a couple of examples. Let's keep it open. Let's hear a couple of examples. 6 is perfect and 28 is perfect. Please note that all the divisors add up to twice of 6. All the positive divisors add up to twice of 28, and also exclude 6, then the rest add up to 6. Exclude 28, the rest add up to 28, precisely. So we can define it in two different ways, like this or that, and they're of course equivalent. But in this notebook, we are going to take this as a definition because we are going to focus upon the properties of this arithmetic function sigma, and we are going to use sigma to prove the next theorem. A positive integer n is an even perfect number if and only if, and then we have the criterion. This. N is a product 2 to the n minus 1 power times 2 to the n power minus 1, where m is greater than or equal to 2 and 2 to the n power minus 1 is prime. That's a criterion, and that'll give you even perfect numbers. The previous examples here, 6 and 28, they're both even perfect numbers, right? So they will fit into this mold. And let's verify that by trying some m values. But before starting, let me make one comment here. We have the definition of the perfect number, and then skipping over to even perfect numbers. What about odd perfect numbers? How about that? What about examples of odd perfect numbers, or maybe some criterion or any theorem associated to odd perfect numbers? Well, the answer is there's no answer. Nobody knows if an odd perfect number exists. So if you find an example of an odd perfect number, or if you prove that such a thing doesn't exist, then you're going to become world famous right away, because it's one of the very, very famous open problems out there. And then a lot of progress toward it was made, but the problem itself is still unsolved. So we're going to stick to even perfect numbers here, because an odd perfect number or anything close to that is too hard for us. And as for even perfect numbers, we have this nice criterion, and this is a necessary and sufficient condition. But here in this notebook, we're not going to prove both of them. We'll prove only part 1, that this is sufficient, which means it works. It works as a criterion, and we can utilize it. As for the other direction, that'll have to wait. We're going to do it in a separate video. Still, before starting, let's talk about how to utilize it in this example. Find the 5 smallest even perfect numbers through the criterion here. Okay, all right. Let's plug in 5 smallest m values, right? M beginning from 2, 3, 4, 5, and 6. Close but no cigar. Because we cannot just plug in, we have something else. 2 to the n power minus 1 should be prime. You have to check that. That's important. That's a key point. You see, let's go back to this expression, product expression. 2 to the n minus 1 power. For m greater than or equal to 2, this is even. And 2 to the n power minus 1, that's odd. That much is certain. Even number times odd number, that much is certain. But this odd has to be prime. So we end up with this kind of computation. So starting from m equals to 1, well, we can start from m is 2, but you can start from 1 as well. Either way, it's not going to work anyway. 2 to the 1 power minus 1 is 1, and 1 is not a prime number, so it fails. And in the end, we get 1. It's not a perfect number. It's not even number either, so anyway, it fails. Plug in m is 2, we get 2 times 3, that's 6. Plug in m is 3, we get 4 times 7, that's 28. And those two are the examples we have here. And then if I plug in m is 4, then what do you get? 2 to the 4th power minus 1 is 16 minus 1, that's 15, and that's composite. 3 times 5, so this one fails. Next, 2 to the 5th power minus 1 is 32 minus 1, that's 31, that works. So 496. Next one fails. 2 to the 6th power minus 1 is 64 minus 1, so 63, which is 7 times 9. So this doesn't work. And then the last one works. 2 to the 7th power minus 1 is 127. And that's prime. And we have 4 smallest even perfect numbers. Actually, 4 smallest perfect numbers, you see. A lot of efforts were made to find odd perfect numbers, whether that exists or not. So a lot of people already tried up to humongous numbers already, and nobody found anything yet. And then nobody proved anything one way or the other. So numbers this small, they must have been tested already. There are 4 smallest perfect numbers. And where's the 5th? Well, you can try m value 8, 9, 10, 11, 12, and finally at 13 you're going to hit a perfect number, because finally we have a prime number here. Up to that point, 2 to the m power minus 1 keep becoming composite, so we all fail. And then we can do more, of course, and here is a mathematical program for up to 50. And then as you can see, if you go down, most of them are false. So they're not really perfect. We have 2, but comes only sporadically later on. So okay, there goes an example problem associated to this criterion. And then we also went through the importance of this condition here, this one being prime. And then also, this is even and that's odd. We went through all those aspects, going through those example problems already, and all those observations will actually help proving this. Okay, let's go to proof. We're going to prove only the sufficiency, which means if n is defined like this, then it's perfect. You don't have to prove that this is even, because we already saw that this is an even number. 2 to the n minus 1 power is 2 to the certain positive integer power when n is greater than or equal to 2. So it's already even. How to prove this is perfect? Well, that's what you have to prove. Sigma of n is 2n. Let's calculate the sigma of this product. And this product, odd times even, actually even times odd, we're looking at 2 numbers that are relatively prime. This one has only prime factor 2, and this one is odd, so they don't mix. They don't share any prime factor, so they are relatively prime. So you can use the multiplicative property of sigma. And that's how you get sigma to the 2 to the n minus 1 power, which I'm highlighting in blue like this, and times this, sigma of 2 to the n power minus 1, which I'm highlighting in red. So we just use the multiplicative property of sigma. Now, let's find out what these blue and red values are. Red value is easier. This is a prime number, you see. Therefore, it has only 2 divisors, 1 and itself. Adding up, you're going to get 1 plus 2 to the n power minus 1. It's that easy. How about blue? Well, we have only 1 prime factor, so 2 to the 0 power, which is 1, and then 2 to the 2nd power, 3rd power, 4th power, 5th power, all the way up to n minus 1 power. That's it. So we can add them all up. That's going to give me a geometric series. And then for this prime, even easier, 1 plus itself. Alright, some simplification is in order. This 1 and -1 will cancel each other out. We have only 2 to the n power. And then as for the geometric series, you can get this from the geometric series formula. As a matter of fact, you're going to have this divided by 2 minus 1, but denominator 2 minus 1 is 1, so we don't need it. So we have this blue times red, and then compare that with the m. 2 to the n minus 1 power times 2 to the n power minus 1. So everything is common except n minus 1 power times to the m power here. So this one down here is twice as of this. So sigma of n is 2n. And that's precisely what we wanted to prove. That completes the proof. By the way, in this computation, the blue part, if you don't want to go back to geometric series and do all those, you can always go back to 2.2 and use this product formula. We have only one prime factor, so discard all those, and plug all those in, and then you're going to get the same result as before. P-value is 2. Okay, that completes part 1 of the proof, which means this criterion works. And in that criterion, we had 2 to the n power minus 1 is prime. That played a significant role. Remember all those? And you should also remember that that's something we already encountered in lesson 4 and lesson 5. Remember that? Primes of the form 2 to the n power minus 1. Remember that? What do you call those? Those are called Mersenne primes. And here's a reminder. Well, this is not really a reminder. We didn't go through Mersenne numbers, I think, in lesson 4. Mersenne number is defined as 2 to the k power minus 1. I changed the character m to k because there are too many m's here. M and m, that's too complicated. mk is easier to pronounce. Now, if mk is prime, then we call it Mersenne prime. That's the term we already went through in lesson 4 and then also in lesson 5. And please remember that most of the humongously large prime numbers were discovered this way. It is easy to prove that k is prime if mk is prime, but the converse is not true in general. Remember doing this as well? I think we did it in lesson 4. Maybe in lesson 5, maybe both, I'm not so sure. But I intend to review it, because I'm not completely sure, as I said before. Okay, all right. Part A of this example problem, calculate all those, and yeah, you can use proof for calculation, and then you're going to go those, and you can see these are not prime for k value 1, 4, and 6, and none of them are prime. And then these are primes, k value 2, 3, 5, 7, they're all primes. Now looking at only those, does it mean mk is prime if and only if k is prime? No, the answer is no, as you can see from part B. M11 is not a prime, even though 11 is prime. So the converse is not true in general. Now finally, prove that k is prime if mk is prime. Alright, assuming mk is prime, we have to prove k is prime. One way to prove that is to use the contrapositive. Suppose that k is composite and prove that mk is composite. So k is a times b, non-trivially, and then express mk as 2 to the ab power minus 1, and then we can use the cyclotomic factorization, 2 to the a power to the b power, 1 to the b power, and then decompose like this, factor like this. One factor, and this part is a cyclotomic polynomial part. So we have a non-trivial factorization. Therefore, if k is composite, then so is mk. Taking the contrapositive, you get what we want. If mk is prime, then k is prime. So even including the review, we completed section 2. except for the last proof, which we'll do in a separate video.